Hello everybody. In the previous video lectures, I covered second-order circuits when there is no input source to the system, such as voltage or current source. Now we'll try to figure out the second-order circuit behavior when there is a step response like input injecting to the system. Okay, so we have a modified, let's look at this, RLC circuit, where we have a voltage source in series with the resistor, but everything is same with respect to a parallel RLC circuit. Let's try to figure out how we can find ODE for this circuit and try to relate this solution with the previous solutions. Okay, so let's look at this. Okay, so again, let's assume that our main variable that we want to find OD is the current of the inductor, such as I is equal to IL. Okay, so this is not nice. Okay, so let's change it. Okay, I is equal to IL, and it's obvious that VL is equal to VC, okay, and let's call it V, which is the voltage of the inductor and capacitor, okay. So if we write KCL, we can see that IR plus IL plus IC, okay, so sorry for that, IC is equal to 0, okay. What is IR? IR, okay, let's call it ground, so we don't need, okay, so let's call it ground. IR is equal to V, okay, so the voltage here is equal to V minus Vs divided by R plus IL is equal to I, and IC is equal to simply C dVc over dt, C times V dot, which is equal to 0, right? C dVc over dt is equal to that. Okay, that's good. So we are just going somewhere else. So as you can see, or if you remember, the only difference is this. Okay, with respect to the previous equation that we found using the unforced RLC circuit. So if we modify it, we will see that it is equal to V divided by R, okay, plus CV dot plus I is equal to Vs divided by R. So which means that the ODE part, or like homogeneous unforced part, is same. The only thing is different is the input source. So what we can do is we can use the original formulation for the homogeneous part, and we can only use the input for the particle solution. Okay, so this is the result, as you can see, consistent with our finding. So in this form, equality is equal to Vs divided by R. If I write OD with respect to I double dot, or the leaving it part, it's equal to Vs divided by RL times C. Okay, good. Let's remember our general format. Okay, so when there's a forcing input, general format can be written in this form, which is not very different from the previous case. As you remember, in the unforced part, we had the same OD, except it was equal to 0. Now it's equal to some forcing component. Okay, good. So again, we can compute V naught, okay, nature frequency, which is same, alpha, which is same. The only difference is we have a different input coming from the external source. Okay, good. So how we can handle the external force, which is very easy. Okay, now again, let's look at this. If you remember from OD classes, okay, so and let's assume that I of t is that we were trying to find, it is composed of two parts, homogeneous and particular. Okay, homogeneous plus I particular solution. We already know how we can figure out homogeneous solution, right? Because based on alpha and omega, we have three cases: overdamped, critical damped, underdamped, and we write that. And the only thing that we need to compute later is the C1 and C2, which comes from the initial conditions. But now we have a particular solution. Okay, and if you remember, particular solution is a solution that can solve the ODE. And in this class, for this part, we assume that particulars, or the input f of t, is simply a constant. Okay, so we are considering step-like inputs. We are not considering ramp, we are considering other kind of things. We will later analyze the sinusoidal inputs in a different framework, but now let's assume that our input is constant after t is greater than or equal to 0. Okay, so how we can I? So we assume that y particular t is equal to some constant, let's call it y steady state or I steady state, it doesn't matter. If we plug into the equation, we will see that omega naught square times y steady state is equal to a times omega naught square. So y steady state is simply equal to a. Okay, that's great. So we already computed that, and it's equal to a. So we can write y of t as y homogeneous of t plus y steady state value, or it's equal to a. That's great. Okay, let's check this. It's raised, you can see. Okay, so y steady state or y infinity is the value of that variable at time goes to infinity. And we know that we can compute this variable without even computing or finding the ODE by just analyzing the circuit, because we know that capacitor acts like an open circuit, inductor acts like a short circuit. We can compute this value without computing the ODE. So what you can do is, you can first find the homogeneous solution, then you can find a particular solution using the steady state knowledge, and later what you are left is computing initial conditions using the computing the coefficient of the homogeneous solution using the initial conditions. Okay, that's great. Okay, let's do it. So the same circuit, but in this case we are given L, C, and R. Okay, so they are given. So input is equal to 4 times U of t. As you remember, U of t is the step input. Okay, so U of t is equal to 0 when t is less than 0. U of t is equal to 4 volts. In this case, no, it's 1 when t is greater than or equal to 0. Okay, so it's like a switch, but the behavior is different. The initial condition of the capacitor is given as 0 volts, and initial condition of the inductor is given as 0 amps. Okay, so let's start with the homogeneous part. In the homogeneous part, what you can do is, you can kill the active sources. Okay, and killing is important because voltage source acts like a short circuit, current source acts like an open circuit. It's important. If you kill wrongly, it will be wrong. Okay, good. So now what we will do is, we will find a homogeneous solution for this circuit. Okay, so we already know that. Okay, this is okay, let's remember. So here, okay, that's great. So okay, can I do that? I can't do that. Okay, so I double dot. Okay, so the OD is in this form, I double dot plus, I think 1 over RC I dot plus 1 over L C I is equal to 0. Let's remember. I think it will be the case. Okay, that's correct. Okay, it's nice. Okay, so this is our homogeneous ODE. Okay, and we write this in this form, y double dot plus 2 alpha y dot plus, okay, omega 0 square y is equal to 0. Okay, so what we need to do is, we need to compute alpha, omega 0, decide on the case of the circuit, and move on with that. So omega naught is equal to square root of 1 over L times C, 0.4 times 0.1. I think it's equal to 5 radian per second. That's great. So what is alpha? Alpha is equal to 1 over 2 divided by RC. R is 1 ohm. C is that. Okay, it's also equal to 5 radian per second. Alpha is equal to omega 0. So it means that we have a critically, oops, sorry for that. What happened? Damped system. Okay, good. So do we have more hints? No, we don't have more hint. That's good. So okay, so when you have critical damped system, let's remember alpha and omega. Omega 0 is alpha is equal to 5, and it's equal to omega 0. In a critical damped systems, we can write y homogeneous t in this form: C1 times e to power st, which is the pole or root, which is equal to minus 5 in this case, t plus C2 t times e to power minus 5t. So this is the homogeneous solution. Let's get the result. As you can see, it is true. Okay, so this is the homogeneous solution for the main variable which we use, inductor current. Okay, so we don't know C1 and C2, and we can only compute it when we compute particular solution and use the initial conditions. Now the goal is finding the particular solution. Okay, good. So in the particular solution, we don't need to use the value of the inductance and capacitance, because capacitance becomes an open circuit, inductor becomes a short circuit, but of course we may need to compute the resistor value. Okay, so in this case, we can technically ignore capacitor because it's an open circuit. Okay, that's great. And we can just make the inductance short circuit, ignore the inductance. So what we need to compute is this. Okay, so this is equal to I infinity, which is very easy. As you can see, that current is flowing in the direction of the convention. So I infinity is equal to nothing but 4 volts divided by R, 1 ohm. It's equal to 4 amps. It should be correct. Let's check it. Okay, it's correct. It's 4 amps. So what we computed is, okay, now we know that, okay, I of t is equal to C1, okay, e to power minus 5t plus C2 t times e to power minus 5t plus 4. So I know this. What I need to do is, using the initial condition, I need to compute the technically C1 and C2. Okay, so this is, so initial conditions can be tricky, okay, for some circuits. You should be careful because we know that inductor current cannot change abruptly. Okay, it should be constant, it should be continuous, okay, when we have a change in the circuit. Okay, and similarly, capacitor voltage cannot change abruptly, okay, because of the continuity principle. But capacitor current and inductor voltage can change abruptly. Okay, it may not, it may, depending on the type of how we apply switches, step inputs, and other kind of that. Okay, so first of all, okay, it's obvious that since IL is equal to 0, I 0 is equal to 0. That's great. So what we need to find is I dot 0. Okay, so what is I dot? Okay, I dot is equal to I dot L is equal to L times d VL over dt. LDI. Okay, sorry for that. Okay, sorry, I just messed up everything. Okay, what is the voltage of the inductor? Voltage of the inductor. Okay, VL is equal to L times di over dt. Okay, so which means that V is equal to L times I dot. I dot is equal to V divided by L. That's great, right? So I know that. But the good thing is VL is equal to VC. Okay, and I know that VC0 is equal to 0. It cannot change abruptly. So in that respect, I dot 0 is equal to 0. So I know everything. Now I can proceed with the facts. So I know that both I0 and I dot 0 equals to 0. Okay, that's great. Good. So I know this, I know that. The remaining thing is just compute the remaining coefficients. Okay, so I0 is equal to C1 plus 0, that's great, plus 4 amps, and it's equal to 0. So C1 is equal to minus 4 amps. That's great. So I need to take the derivative. I dot 0 is equal to, okay, that's great. So this is equal to minus 5 C1 e to power 0. So that's it. Okay, plus I take the derivative of this. So when I take the derivative of e to power minus t, t will remain there, so it will be 0. So I only need to take the derivative. So t is equal to c2, t is equal to 1, e to power minus 5, 0, it's equal to 1, it's just c2. So derivative of 4 amps is equal to 0, so it's equal to 0. So c2 is equal to 5 times c1, and it is equal to 20, I guess, right? So I guess it's 20. Okay, exactly, minus 20 amps. So I of t is equal to 4 minus 4 e to power minus 5t. Okay, minus 20 times t e to the power minus 5t. Of course, the unit is amps. Okay, that's it. So we technically follow the process very nicely and able to compute the solution in a couple of different steps. Okay, very good. So let's look at the result. It should be correct. As you can see, it's correct. Okay, so let's remember what we did. Okay, so we started with this. Okay, we have a circuit. Okay, I can even clean everything. Let's do that to give some space because it's important. Okay, so we are giving that we have a circuit. We know the variables. We know the input type, we know the initial conditions on the inductor and capacitor. In some problems, you may need to compute that, okay? So under these assumptions, what you do is this. Okay, so first kill the voltage source. Okay, you don't need to do that, but this is one way of solving this, okay? Kill the voltage source, okay? Find the ODE, and compute I homogeneous of T. Okay, so, or it can be V homogeneous T, where we consider the capacitor voltage, and it should be given to you in the problem. Okay, so once you compute the homogeneous solution, the format, of course, you will have some C1 and C2. You can proceed to the particle solution. Okay, so in the particle solution, what you do is you need to compute the variable's steady state value, which is the current now, when t is going to infinity. In this case, we know that capacitor will become, okay, so capacitor will be in an open circuit. We just remove that, okay, in the circuit. Inductors become short circuit, okay, that's good. So under these conditions, compute the corresponding variables steady state value. It's I infinity. Okay, so what we computed that, okay, when you compute this, let's call it, it's I of t, it's equal to homogeneous t plus I infinity. Okay, so this is given, okay, this is known, but in a format way, because we have C1 and C2. In the other case, what you need to compute is compute I0, okay, this is obviously given, and I dot 0 is equal to, okay, so computing initial conditions can, you may need to do some sort of analysis to compute all of the initial conditions. So in general, one of them is very easy, okay, but the derivative is tricky. You may need to use other variables, and you need to analyze the circuit under like Kirchhoff voltage law, current law, and continuity principles of the capacitor voltage and inductor current. Okay, once you compute this, you can compute C1 and C2, and you are finally have obtained a result. Okay, so in general, I will recommend you to at least check that as t goes to infinity, when t goes to infinity, I of t should go to the I infinity, which is exactly this goes to 0, this goes to 0, it is going to 4. And one of the easiest ways of checking your solution is, let's check I0. Okay, taking the derivative maybe like takes some time, like 1 or 2 minutes, but taking as t goes to infinity, or checking I0 is very easy. As you can see, I0 is equal to, in this case, 0, because this is 0, this is 4, 4 minus 4 is equal to 0, which is consistent with our initial conditions.